This is the solution video for question 6 from section A of the 4th sample test for CSAT. In this question, we're told about this sequence fk, where fk is such that fk is equal to fk minus 1 plus fk minus 2, where f0 is 0 and f1 is 1. So this behaves a lot like a Fibonacci sequence. And given this, we define the series Sx to be the sum from k equals 1 to infinity of fk over x to the k for x greater than 2. And given all this, we're asked to show that Sx is in fact x over x squared minus x minus 1. The first thing to probably say about this question is that we are meant to implicitly assume that s of x is actually finite, that this sum does in fact converge. Now, this isn't particularly obvious, at least from this form. You can indeed prove it by using difference equations, they're called, but essentially what you can do is you can construct a general formula for a fk element of this sequence and then look at fk over x to the k as a geometric progression and show that when x is greater than 2, the ratios of the bits you need to sum up are all less than 1. So that's essentially how you can do it, but we don't have to worry about that, and that's far beyond the scope of this question. So we're just allowed to assume this converges. So what are we going to do? Well, the only thing we've really got is fk is equal to fk minus 1 plus fk minus 2. So we're going to have to use this and substitute this information into here somehow. So fk over x to the k is equal to fk minus 1 plus fk minus 2 over x to the k. The important thing is, though, that k has to be greater than or equal to 2 here, because if k was 1 or 0, fk minus 2 makes no sense. So this is what we've got. Now, clearly substituting this straight into here isn't going to particularly help. So what we're going to do, well, let's try writing this as this. So 1 over x, fk minus 1 over x to the k minus 1 plus 1 over x squared, fk minus 2 over x to the k minus 2. Now, the reason we've written it like this is that these terms look a lot like these, but with k decreased by 1 or 2. So hopefully by substituting this information into here, we can get s of x to equal some expression that contains s of x, rearrange that, and get our result. So what could we do? Well, if we're doing the sum, let's substitute this information in. So k equals 1 to infinity. This only holds for greater than or equal to 2. So firstly, 1 over x, let's get rid of that first. And then our sum from 2 onwards. And we have 1 over x, fk minus 1 over x to the k minus 1, plus 1 over x squared, fk minus 2 over x to the k minus 2. So this is completely equal to this. And you can probably see where this is going now. That if we drag the 1 over x out of here, or the 1 over x squared out of this part of the sum, we have something that looks very close to s of x. Indeed, so we have 1 over x plus 1 over x, so we'll just replace this by s of x, by the way. 1 over x, sum from k equals 2 to infinity, fk minus 1, x to the k minus 1, plus 1 over x squared, and move the sum across, fk minus 2 over x to the k minus 2. So now you'll notice that this is just Sx, because summing k minus 1 from 2 to infinity is the same as summing k from 1 to infinity and having k's here instead. So this is Sx. What about this? Well, this is Sx as well. So this is the same as summing from 0 to infinity fk over x to the k, but we know f0 is 0. So that's the first 0 term is not, it has no impact. So it's the same as summing from 1 to infinity fk over x to the k, so this is Sx2. So we have s of x is 1 over x plus 1 over x s of x plus 1 over x squared s of x. And now we're essentially at the answer. Since we can times this through by x squared, to get x squared s of x is equal to x plus x sx plus sx. Group the sx's together, we have an x over x squared minus x minus 1, divide through by x squared minus x minus 1. And we have our x squared equals x over x squared minus x minus 1, exactly as required. And so we've shown this and we're done.